covering part of the homework. So I think it'll help clear up the homework, which will just be graded on presentation and completeness that you gave it your best shot. Let's turn that in. Since some people will have their own paper here, we're going to go ahead and fold this. Please get your heading in the upper right, after you fold, upper right corner of the heading of the paper. So we will be talking about part of the homework as part of today's lesson. Pass it up. Anyone need their quiz? Anyone come in late? And there's homework from Mondays. So Monday's homework is coming. Make sure you see the stacks for Monday's homework. There's 2 different stacks, one for each recitation. Do I have all today's homework coming in? One right here. Any more homework? It is due now. Not at the end of class. Okay. So we're talking about accumulation, and our goal here is creating accumulation functions mathematically. So let's review what accumulation is, and let's talk a little bit about the idea of accumulation function. So the idea of integration is that the value or total change of a quantity can be calculated. So now, without reading your notes from last time, who remembers how we find the value or total change of a quantity if we're talking about doing it by integration? Remember what this is about? Calvin?
Sum notation.
What's that?
Is it sum notation?
Well, that's what we use, but that's not the idea behind it. Yeah, so we're going to use summation notation. So it has to do with summing things together. What kind of things are we summing together?
Isn't it just
Yeah, summing little bits, right? So integration is finding the value of a quantity as a sum total of many little bits of change. Okay, and that's what we said was accumulation. So what is this thing, an accumulation function? So an accumulation function is finding this total quantity. It's a quantity function, but it's built from a framework of accumulation. So the way that the function works is by accumulation. The way that we get this total quantity is through the process of accumulation. Okay, so taxes on X dollars of taxable income. So this is the idea of a function. You're going to plug in the number of dollars of taxable income, and it'll tell you what your taxes are on that. But as an accumulation function, that function will calculate it by adding up the little bits of tax to get up to whatever taxable income you have. Okay, the height of the ball after X seconds. This is the height function. You plug in X seconds, it'll crank out the height. But as an accumulation function, the way that it cranks out that height is by adding up all the little changes in height along the way. So what we're going to be doing is constructing these functions, these rules that give us the total quantity for any input. And the way that it gives us that total quantity is bit by bit by bit. Okay, so in your homework, you were given this was a bacteria, rate of change of bacteria. So we could call that R sub B. And the input was the number of hours, is that right? Number of hours elapsed, and then this was rate of change. Okay, so first we want to compare this function to, before we start getting into your homework, how is this rate of change function different than, remember our basketball racket function? The rate of change for the basketball? Looked like this. So, yes, the bacteria function goes up and down and up and down, and the rate of change of the racket function is always going up, generally, but there's a fundamental difference between kind of what's going on in this rate of change function and this rate of change function. What is the major difference? You tell me.
The basketball rate of change is always constant, like bit by bit.
Yeah.
And the bacteria rate of change is not constant.
Did you hear what she said, Ben? Is that what you're going to say? Yeah. This is based on what? Constant rates of change in each interval. So yeah, they're jumping, but in each interval, those rates of change are staying constant. This, what's happening to the rate of change here? It's always changing. Always changing. Okay? So there's kind of like good and bad to both. So can you, in terms of thinking about what these represent and working with them mathematically, what's good or bad about one or the other? What are your observations about these? Yeah, Joe.
The curved one might be more accurate to real life, whereas the other one is not as accurate to real life.
Okay, let's think about this. Could we create a rocket that's going to, against gravity, force a perfect constant rate for the basketball and then instantaneously speed that rate up to something faster and keep it constant? So is this realistic? Okay, it's similar. I talked about how it's similar to the World War II bombs, okay? But it's fictitious, okay? It's impossible to really have a situation like this. Whereas, what about this? The rate changing, does that, continuously, how the bacteria is growing or dying off, that rate is always changing. So yeah, so this is kind of like more of a real situation where this is kind of a fictitious setup. It's like a scenario that we just kind of make up, and it's really not practical. So, why? Why do we spend all our time working on this if it's not practical? Nick?
So we can understand the base concept behind it, so then we can apply it to the more complicated one.
Okay, true. And so what did this afford us? What did this allow us to do? Was it easy or difficult to calculate changes in height in the basketball with this rate of change function?
Easy.
Easy, because if they're at constant rate of change, we can apply what principle? Changes in height were proportional to in time, right? Proportional to changes in time, because we had constant rate of change. With constant rate of change, changes are proportional, and so therefore, our change in height is always a constant times our change in time. More specifically, what was that constant? What is the rate of change? What do we call that? It's height with respect to time. That was the speed. That was our velocity. So each little change in height we could easily calculate by constant rate of change as speed times change in time. So it's very convenient. What about here? As soon as a little time goes by, what happened to the rate? It changed. And then a little more time goes by, the rate changes again. It's like, wait, stay constant for a second so we can make a calculation and get a change in bacteria. But it won't, right? It's just going to constantly change. So this is unrealistic but very convenient for calculation. This is realistic but much more difficult to at first glance, much more difficult to say, okay, let's come up with, how much bacteria there is at a certain time or a function for that. But what Nick said is true. We're going to take this principle and we're going to apply it to the function where the rate changes. And this is kind of what you did in your homework. So in order to apply this principle of constant rate of change to this function with a changing rate, what did we do? What did you do in your homework? Okay. So you talked about intervals. So what you did intervals of 0.4 first, so you got 0.4, 0.8, 1.2, 1.6. Oops, that's wrong. Okay. So you had these intervals, and what would we do with those intervals? Yeah, Will.
In each of those intervals, you pretended that there was a constant rate.
Did you hear what he said? I love that. We pretended. That's exactly what we did. We pretend that in each interval there's a constant rate, like the rocket basketball, because then the math is very convenient. So how do we pick the constant rate for this first interval of 0.4? We looked at what? Or what did you look at? How did you pick the constant rate? Did you just pick 500? Would that be good pretending? 1,000? Negative 1,000? No, these are not good. Lauren?
You can take the starting point and the ending point within the designated interval and just create a new slope for it.
Okay, so are you kind of talking about like this?
Yeah.
Yeah, but then still, even though that's a straight line, it's still a changing rate. So it's even though that's the linear rate, and so we don't have that convenience of we want truly a constant rate. You tell.
At the point 4, you drop the line down to meet the graph, then you go to the y-axis to find the y value.
Okay. Yeah. So what you did is you looked at the right side of the interval and you took the actual rate at the right side of the interval, and then you said the whole interval will have that constant rate. And then you did the same thing at point 8. You said, okay, what's the rate at point 8? We're going to make that the rate for the whole interval. Okay, and then 1.2. It's up here. We'll make that the rate for the whole interval. And then 1.6, a little bit below 0. We'll make that the rate for the whole interval. And then at 2, what's the actual rate? We'll make that the rate for the whole interval. Okay, so what this is called a step function. So you created a step function we're trying to so maybe not pretend, but we're trying to simulate the actual rate function with constant rates. We're trying to simulate the actual rate of change function with constant rates. And so the actual rate we called RB of x. That's the changing rate function, the purple one. So my question is, what is step x, step of 1? I'm not asking for a number, but I'm asking for how do we get what that number is, or how can we represent what rate of change we have in our step function at 1. Where does that number come from? So yeah, so we can come over here and look and see, oh, okay, it's about 150. But where did the 150 come from? How can we represent? Where did that 150 come from? Any idea? Just out of the blue? Lauren? We have it. RBX.
Oh, okay.
Okay, so yeah.
So then you just say RB of 0.4.
She said it's RB. Step 1 was RB of 0.4. Agree with that? Agree? Yeah? What's RB of 0.4? Here's 0.4. RB of 0.4 is this value here. Is that what step of 1 is? What's step of 1? I like using the function. That's good.
RB of 1.
Is it RB of 1? Because RB of 1 is about 0. What is it? It's RB of, see, it came from the right side of our interval. So it's the actual rate at the right side. So step 1 is RB of 1.2. Do you see? It's the actual rate at the right side of the interval that we're in. Okay? So more practice. What is step of 0.1? How do we get the rate of change in our step function at 0.1? Where does that number come from? Jack. He wants RB of 0.4. Agree? That's it. Okay, what about step of 1.9? Where are we getting step of 1.9? It's not 2. RB of 2. That's different. So it's not 2. 2 is the x value. It's the rate at 2. Right? So the step value at 1.9 is the actual rate at 2. What about step of 1.601? Roman.
RB of 2.
Still RB of 2, because that's in that same interval. Right? 1.601 is about here. Where does that rate come from? It comes from the actual rate at 2 on the right side of our interval. Okay, so for your homework, I need to make some room here. So for your homework, you actually did some calculations here on this. So what did the bacteria population start at? 10,000. So it started at, so at x equals 0, it started at 10,000. And now with this, we can calculate what the change in bacteria was for a step function for that interval. So how much did the bacteria change at this? So we say this constant rate is about negative 500. So in those first 0.4 seconds, how much did the bacteria change? Adria, what do you think?
I'm saying around negative 1,250
1,250. And how'd you get that?
by doing change in y over change in x.
Okay, change in y over change in x is the rate. That's what we have. We have the rate. It's negative 500. So how are we going to get changes in change in our quantity at constant rate of change, Connor?
And to get the change, you just times the negative 500 times 0.4.
Right, it's going to be our k delta x. See, it keeps showing up. And k is
Negative 500.
our rate delta x. So the rate of change in negative 500 says that bacteria is always changing 500 times, decreasing 500 times as fast as time is going by. So if you have this much time that goes by, you're going to have negative 500 times that in bacteria change. So what is that? 200? Negative 200. Okay, so according to our step function, what is the new bacteria population at 0.4 hours? 9,800. It went down 200. You see? Okay, so then at 0.08, in the next 0.4 seconds, how much does the bacteria population change? A rate is about negative 200 for a change of 0.4 would make go down. Is that going down about 80? So delta B for this was about negative 80, right? The rate times the change in x. So what would we have now? After 0.8 hours, 9,720, because it went, according to our step function, it went down 80 at 1.2. So we said this was about 150. 150, so the change in B for this would be 150 times 0.4. Using our constant rate of change, it's the rate times the change in x gives us the change in y. And is that 60? So we're going to go up 60 now. 9,780. Check my math. Okay, just 2 more to go. 1.6, 2.0. So this is, we'll say, negative 50 times 0.4. Is that negative 20? It's going to go down 20. 9,760. Finally, it's going to go down, we'll call this negative 400. The change in B for the last interval is k times the change in x. Negative 400 times the change in x. Is that 160? So 9,600? So what did we just do? I just created an accumulation function. Is it the true accumulation function of the bacteria? Is it the true accumulation function of the bacteria? No, why not? Because it was based on this step function that's trying to simulate the actual rate of change. Okay? So it's not accurate. It's the concept is right, the idea is right. Okay? But the true rate of change is constantly changing, and we use the step function instead. So this is the idea of the accumulation function, that if you plug in the amount of time now, it's going to tell you the accumulation of bacteria, or the amount of bacteria at that time. But we built it on the idea of accumulation, bit by bit, 0.4 hours at a time. Okay, so that was to help you kind of, does that help with the homework? Does that clear things up? Any questions about the homework or about this? Yeah, you bet.
For parts C and D, when it said like to 2.5 and then 3.5, we're supposed to calculate an actual value because it said assume 2.5 was unknown. We're supposed to find that unknown value in that.
So you went from here to here?
Yeah, in point two. Well, and then it said like a geometric.
So it was saying if you didn't know what the population was here,
Right.
and you did that, you did the same process of finding the changes on each, and you added those all up, what would that represent for 2.5 to 3.5?
Just do your change in bacteria.
Yeah, without knowing what you started with, all you could calculate is how much the population changed over that time.
Okay.
Does that answer it?
Yeah, but there was just this one on the part where it said like the geometric midpoint or something like that. Geometric.
Oh, so rather than using the right side, you would, for each interval, you'd look at the function value at the middle of the interval, and then you'd call that the rate, the step, or the rate for that whole interval.
Was there a reason behind that, or just?
Just because we'll do it different ways.
Okay.
Yeah, you'll sometimes use the right, sometimes use the mid, sometimes use the left.
Alright.
Yeah. So just practicing something different. Other questions about this? Okay, hopefully that clears it up, and then it bridges us to this idea of building an accumulation function based on little bits of change. What do you see? Talk to me. What's being represented here? Yeah, Saskia.
It's like it's another step.
Another step function. How is it? Is it different or the same as ours?
It's different. It's using no.
It's got smaller intervals.
Yeah.
Yeah. What's the width of these intervals? Instead of 0.4, now it's 0.1. There's also another difference about it. Anyone notice?
What are you using?
Lauren.
The start of the step is at the beginning of the interval.
We're not using the left side anymore, right? We're using the right side of the interval to pick off the actual rate that will be the rate for that whole interval. So let's practice. So what about, this is our new step function. So tell me how to, so this is still RB of x, the actual curve is RB of x, okay? So what is step of 0.73? I'll just give you a couple here. So everyone think about it themselves, and you can practice. So step of 0.73 is right here. If we plug 0.73 in, what do we get for the rate?
RB of 7, 0.7.
He wants RB of 0.7. Agree? That's it. Because now you're going to go to the left end, and this is the key here. We're going to be working on this. You're going to go to the left side of that interval. That's the actual rate now for that whole interval. So we could say that's equal to step of 0.78. Would you agree? 0.78 is about here. It has that same rate, which is the actual rate at 0.7. Okay, step of 2.19. Mary. So here we are. There's 2.19 right there. So I'm asking you to represent it, not to guess what the nut value is, but represent it like we've been doing. So 2.19, the value of the step function at 2.19 is the same as what? Crystal. RB 2.1. RB 2.1 is not drawn very well. It's over here. So RB 2.1 right there, the whole interval is going to have that same rate of change, so 2.19 will fall under that interval. Okay, step of 2.81. Andrew.
RB of 2.8.
That's it. Okay, so here's what we need. What we need is a way, when things get more complicated, of getting this value, this left x value, of the interval that we're in. That's the key, because then we're going to plug that into our rate function, and it'll give us the constant rate in that interval. And so when delta x isn't so nice, and maybe we don't start at 0, coming up with this left-hand x value is a more complicated thing. So we want a mathematical way of getting this left x value of the interval for the x value that we're in. So, are you glad your intervals were 0.4 in your homework? Okay, so what does this represent? These step rates every 0.1 interval, all the way from 1 through 36 intervals. Okay, and like we did, we made a table. You can make a table. Starts at 10,000. Using those rates of change, you get to find out in each tenth of an hour how much the bacteria population changes, and you can set up this accumulation function. Okay, so this function tells you what the bacteria population is at any given tenth of an hour, or an estimate of it, through the idea, the framework of accumulation, bit by bit, tenth of an hour by tenth of an hour. And then we could graph that. So starting at 10,000, bacteria population going down, then up a little bit. Okay, so conceptually it's fine. It's too much work. It's inaccurate, we said. So we want mathematics to make it so that the graphing calculator can do it for us. The computer can do it for us quickly and accurately. And the first part of that is what we talked about. So every value of the step function within this interval has a value of r at the left end of the interval. Step x equals r at the left end of the delta x interval that x is in. So we need a method to calculate that left end point. Okay, so that's our goal. That's our first goal anyway. For building these accumulation functions, we need to get that r value when the numbers aren't so nice. There's going to be lots of extras, just leave them in the back. And if there's not enough in the row, just pass left and right back there. Okay, so what I'm representing here is a graphing calculator file. And we're just working on the x value. So what this shows is our value of a is the starting point. So here a is -1. So for the first one on the top of your worksheet, you can plug in that a is -1. So that's the starting point. Okay, then each red dot signifies the change of an interval. So these intervals are 0.8 long. Delta x is 0.8. And just like we were doing, so here we are, we're picking, this is our input x. And what are we interested in? We want to know then what's the x value of the left end of the interval where the input falls. Because we're going to have the same rate of change for this whole interval, which is determined by the x value at this right here. So when we land in this interval, we want to know what rate of change we have. That will come from the left end of the interval. Does it make sense? So we need a mathematical way of coming up with that value. So what I want you to do is figure this out. So what is the x value of that red dot right there, or the left end of this interval? What is the x value of that? When you think you've got it, raise your hand. Everyone work on it. So when you think you've got it, raise your hand. If a is -1, starting point is -1, change in x is 0.8, and my n is 2.4833. That's the n. The n is our input x. Right, sorry. Yeah, that's our n. Oh. Is the task clear? Do you know what you're doing? So everyone's going to think about it, figuring out what. So any way you can do it, any way you can figure out how to get the x value of the left end of that interval. You think you got it? You think you got it? So a couple of, okay? Everyone think about it and work on it. Yeah, you can use a calculator, or if you want to get out a graphing calculator and use it as a computer or computing device, you can do that. N is this number that's falling in that particular interval. So that's like when I was saying, what is step of such and such? It's 2.4833. 2.4833. So you're figuring out what is the value of the left side of that interval with the right question mark. Good. Okay. So the answer is just make x value again. So just use these two values. Get it? So write out, so you got some space there. Lots of you just kind of figured it out and came up with an answer. Write out your thinking, or your mathematical thinking. So write out the computation that you did to get it. Okay, write out the computation that you did to get it. You got it, Joe?
No, I need help.
You need help, okay.
So, alright, if I understand this right. This is going from there.
Yep. 2.8.
A is the starting point of that.
That's right.
Then N is basically what we're trying to find the interval, right?
That's the blue line. So n is 2.4833. That's like what we're going to plug into our step function.
And then we're trying to find what the interval is from.
We want to know what's the x value on the left end of that interval because that's going to determine the rate for that whole interval. So what's the x value right there?
Oh,
We want the x value of the left side of the interval.
so.
So,
Which is still right.
yeah. So that's it. X value of the left side of your interval, just the x values. There's no quantity involved here. It's just working with the x, right? We don't have a rate of change. We don't have any quantity. You know, it's just the one quantity we're working with, the x quantity. We're asking what's that x quantity on the left side of the interval that we're in. So Richard, tell me what you did.
I started with my starting point of -1.
Start at -1.
And then each interval is 0.8 units.
Okay.
And there's 4 of them to get to the location I want to be at. So I just multiplied 0.8 times 4 and then added that to -1 to get my answer.
So we start at -1 and then we're going to go 4 intervals, and each interval is 0.8 long. So what does that number 4 times 0.8 represent? Change from -1 to the place we want to go. It's that distance from the left, from the start to the end. It's going to be 4 intervals of 0.8, but we start at -1, so you get? Does that make sense? Anybody have a question? All right, I'll give you new values here. Oh my God, 2. Okay, so n equals, so here we are coming into our interval at 10. N equals 10. What are we asking for? The x value of the left side of that interval where n equals 10 is. When you get it, raise your hand. And then if you have a question, you gotta like call me over. Jack's got it. Richard's got it. Adrian's got it. Tom, you got it? Sam's good. Okay, we got lots of people getting it now. Here's where we're moving towards though. How can we mathematically get, say, a computer to do that counting for us? We can't type in a graphing calculator. Count the number of intervals. We need to tell it mathematically how to do that. So that's for those who are, if you're getting it, how can we mathematically tell graphing calculator how many intervals that is? That's our next step in doing this. Okay. Let's see. Isabel, did you get this one? No? Jimin? Tell me.
Delta x times n, and then you subtract
Times n? Are you sure? What do you want to multiply delta x by? Yeah, how many intervals are there? Maybe there are. I think there's less than that. 6. So from the starting point to where we want is 6 intervals, right? And we multiply that by delta x. Is that the answer? Plus our 2.1, which is our a value. So we want a plus delta x times the number of intervals. What you should get something just greater than 9. What do you get? 0.2? 1.2. Which looks in the ballpark, right? So here's our general idea. A plus delta x times the number of intervals. The question is, mathematically, how can we create a formula that gets this number of intervals? Any ideas? Ben?
N minus a divided by delta x.
Nice. Okay. So explain that. Explain what you're talking about. Can you? So what's the n minus a mean?
It's just putting. It would just basically put a at 0. It would just basically move it back, so then you would find out. So then you could take that number and divide it by the number of. You divide it by the change in x, and you'll have the number of intervals plus the section of the last interval.
Okay. Excellent. So n minus a gives us what? Doesn't n minus a give us this whole distance from our point to the starting point? Okay, so that's n minus a. If we want to know how many intervals there are, how are we going to get the number of intervals that n minus a is made up by? We're actually cutting it up into intervals of size, what? Delta x. So if we, like you said, if we divide by delta x, that's how many intervals, but we're going to have a fractional amount, right, at the end? We're going to have this additional amount that we don't want. So what is, for this particular example, what is n minus a over delta x? 10 minus 2.1 over 1.17. What is it? 6 point? Tell me? 7.5. So what's that saying? It's saying if we cut that distance, if we cut it up into intervals of size length 1.17, we'll get this many of those intervals. But we don't want it all the way to here. We want it to there, which is going to be 6. So we want the number of intervals over the length, but then we want to like chop off the decimal. So we get the whole number of true intervals. So what we can do, this is called a floor function. It takes whatever number you put into it, and it gives you the next lowest whole number. And we denote that this way. You put like bars, but like with little, like for floor, like that. So this will calculate the number of intervals from A all the way to N, but then we don't want it all the way to N. We want it just to the left side of that interval. So we got to chop off the decimal and make it the next lowest whole number. And that's what, so when you put 6.75 into the floor function, it returns 6. So then what does our formula become? A plus delta x times the number of intervals, which is our floor function of n minus a over delta x. That will give us the x value of the left side of the interval that we're in. Okay, the next homework's going to be due Monday. So you can study for your quiz on Friday, but you should, it would not be a bad idea to get started on the homework before Friday also.
Question about the homework and why it was 5 points.